Lecture 12 is Stokes theorem in exterior algebra. To derive the Stokes theorem in exterior algebra, we will bridge the classical version of theorem from vector calculus to the language of differential forms. Now, this is from the classical mechanics, okay? The Stokes theorem, the partial f dot dr. You see, this is rotational of f dot and ds, where f is the vector field, s is an oriented surface with boundary. This is partial x, s. Recall that nds is the oriented surface element. Oriented means that the unit vector n points outward, okay, for the surface. That's exactly as what we did for the Gauss theorem. Now, statement, exterior algebra. Let omega belong to one form, and on this case, on oriented to the surface S, that S belongs to the manifold M with a boundary. Now, the integral of in the boundary of the one form omega is equal to the integral of the surface of d omega, which belongs to two form. Now, instead of developing for each step, you see, we will extend what we did for the Green theorem, okay? And I will show right here. So, from the Green theorem, we saw that this is 0, 0, dx dy. You see, remember that dx dy, okay, this is a unit vector k. You see, the unit vector k is normal to the xy plane. Exactly, that's for the Green theorem. So this is a vector, unit vector k. Now we extend this for the determinant over here, just to recall that the blue one I cross here, this is exactly the Green theorem. Okay, so I'm extending for the 3D, three-dimensional. Then the rotational, analogous, okay? Analogously, then they derive this, partial x, partial y, partial z, f1, f2, and f3. This is determinant, okay? Just quite easily. Then recall that this is a unit vector I, unit vector j, unit vector k. From the vector calculus. You see, it's quite straightforward that to do this. And this blue one here, you see, is the Green theorem. But this will be 0 and 0. This is a Green theorem. So there's an extension. I think it's simpler, okay, if you derive this extending the Green theorem. So next lecture, okay, this I will present a numerical example just relating this integral here on the boundary S to the surface S, oriented surface S. Okay, that's it.